we are going to see about uniform boundedness theorem. It is a very important theorem. So it is otherwise known as Banach-Stein's theorem. So B is the Banach space, N be the non-linear space. B is the Banach space, Ti be the non-empty set of continuous linear transformation of B into N. So into means that one of the term in the domain has no preimage. So Ti is a non-empty set of continuous linear transformation of B into B dash with the property that norm Ti of X is a bounded subset. If Ti is a non-empty set of continuous linear transformations, Ti of X is a bounded subset of N for each vector X in B, and norm Ti, that the sequence of norm Ti is a bounded set of numbers. It is so this bounded set of numbers means norm Ti is a bounded subset of B comma N. Okay, B of B comma 1. We have the following. We know that Ti is the transformation from B to N. Ti is the continuous linear transformation such that Ti of X is a bounded subset of N for each X in N. Okay, we have to prove that Ti is bounded as a subset of B of B comma N, which is the set of all linear transformation from B to N. Okay, for that we need to consider the integer, positive integer. Hence we defined as Fn equal to X such that X belongs to the Banach space and B is the bounded. It is a Banach space means continuous linear transformation. We know that Ti is bounded subset. So norm Ti of X is bounded, so less than or equal to N for all I. Then to prove each Fn is closed subset of B, we have to prove that closed bounded means there exists a closed, so Fn is a closed subset of B. So X belongs to Fn means Fn exists norm Ti of X less than or equal to N for all I, and then double implies Ti of X belongs to this belongs to Ti of X where it lies that Sn star. So where Sn star denotes the closed sphere centered at origin in N, because if X here lies means B and it is N. So our T of X is this. If it is means that is surrounded by the sphere, that is Sn star. Okay, where Sn denotes the closed sphere centered at origin of N and radius N. So if Ti of X belongs to Sn star, so X belongs to Ti inverse of Sn star. So definitely X implies that Fn also belongs to X belongs to Fn, means Fn belongs to that. Definitely X belongs to this means Fn is belongs to the intersection of some closed sphere. So if Ti is now each Ti is continuous, Ti Sn star is also closed. If Ti is continuous means if Sn star is closed, if T of Sn star is closed, then T inverse also closed. Okay, we know that T is a continuous, Ti is continuous. So Sn star itself a closed sphere, and then transformation of Sn star is also closed, and the inverse also closed. So intersection of all the inverse terms also closed in for all I. So each Fn is the, if it is all of them are closed, so Fn is a closed subset of B. So Fn is a closed subset of B. We have proven that Fn is the closed subset of B. Then what we do means we have to prove that B equal to union of N equal to 1 to infinity of N. So if B does not belongs to means X belongs to there exists X belongs to B means X does not, because both are not equal. Okay, so there exists X belongs to B means X does not belongs to Fn. X does not belongs to Fn means we already know the condition. X belongs to Fn means norm Ti of X less than or equal to N. but norm Ti of x is greater than, because it while x, if x is not belongs to, so it is opposite of that condition is norm Ti of x greater than n. The set norm, the set Ti of x is not bounded, so it will contradict our hypothesis. So Ti of x is bounded for each x. So b equal to union of n equal to 1 to infinity f n. Okay, we have proven this. Next, what we have to prove means, by using a Bayes theorem. Bayes theorem means if a complete metric space is the union of sequence of subsets. So the union of sequence of subsets, then closure of at least one set in the sequence. In this sequence, the closure of at least one set must have a non-empty interior. So non-linear space is a metric space. So B is a Banach space, so it is a complete metric space, and the union of the sequence, then the closure of at least one set in the sequence is have a non-empty interior. So B is complete, and the union of subset have subset, and hence by the theorem there exists an integer n naught. So there exists an integer n naught that will present in the sum of the closures of f n naught. So f n naught closure has a non-empty interior. By fourth condition, we know that Fn is a closed subset of B. So but from 4, Fn naught is the closed subset of B. So closed means that Fn equal to Fn bar. So Fn has a non-empty. Fn also has the non-empty interior. So x naught be the interior point of Fn naught. So there exists the closed sphere. Interior point means that definitely it will have a closed sphere. There exists the closed sphere S naught centered at x naught of radius r naught. Okay, closed sphere of S naught centered at x naught of radius r naught or greater than 0, which is contained, is definitely contained in Fn naught, as Fn naught is closed. So S naught is contained in Fn naught. S naught can be written as x belongs to B means, we take the another point, norm of x minus x naught less than or equal to r naught. In closed unit sphere, we can define as s naught equal to x belongs to capital B, Banach spaces, norm of x minus x naught less than or equal to r naught, that is contained in Fn naught. So x belongs to s naught means that is contained in Fn naught. So x belongs to Sn naught, that is contained in Fn naught, which can be written as norm x minus x naught less than or equal to r naught. So norm x minus x naught less than or equal to r naught means x belongs to s naught, that is also contained in f naught. So according to the f naught condition, we wrote that f naught is ti of x. So here norm ti of x less than or equal to n naught. If it is n, there will be n. If it is n naught, there will be a n naught. By the definition of f, x belongs to both s naught, x belongs to f n naught. So if it is x naught means, if it is s naught means we have one form, and if it is f n naught means we have one form. Okay, then what we have to do means, choose a z equal to r naught y, where norm y less than 1, where it is a norm y less than r1. So norm y is less than 1, norm z equal to norm r naught y. R naught is a scalar radius, so r naught norm y, it is now r naught norm y is less than 1. We have choose z equal to r naught y, where norm y is equal less than 1, so less than or equal to r naught. But we take z equal to z plus x naught minus x naught. So norm of z plus x naught minus x naught is less than or equal to r naught. Because z is less than or equal to r naught means we to choose z as, so z plus x naught minus x naught also less than or equal to r naught. Then we know that form, that is x minus x naught less than or equal to r naught means x belongs to s naught. Here z plus x minus x naught less than or equal to r naught means z plus x naught belongs to s naught, that is contained in f naught. According to the f naught conditions, norm ti of x, here x is z plus x naught less than or equal to n naught. So x naught belongs to s contained in f of n naught. implies that we already know that x belongs to s naught contained in f n naught means norm of ti of x naught less than or equal to n naught. So norm ti of, we take that y, norm ti of y is z by r naught. So norm of ti of z by r naught. So take take 1 by r naught outside means ti of z. So 1 by r naught norm of ti of z. Ti of z instead of z we can replace as z as z plus x naught minus x naught. So 1 by r naught norm of ti of z plus x naught minus ti of x naught less than or equal to 1 by r naught norm of ti of x plus x naught plus minus ti of x naught. In the norm both negative term will be positive. So norm ti of z plus x naught plus norm ti of x naught, then it is less than or equal to, if we take split the norms, that will be definitely less than or equal to 1 by r naught. That is, this will be, we know that ti of z plus x naught less than or equal to n naught. So instead of that we can replace n naught plus ti of x naught is, we know that ti of x naught is n naught. So 2 n naught by or not. So what we have to prove means, we have to prove that ti is bounded. For that bounded, it will be that norm t is less than or equal to some constant value. For that only we are proving this. So norm ti of y is less than or equal to this term 2 n naught by r naught where norm y is less than 1. Then we take the supremum. Basically we prove the bounded condition based on supremum. Supremum is norm ti of y, uh, y less than 1. Instead of ti of y we have 2n less than or equal to, which is less than or equal to 2 n naught by r naught. So norm ti of x less than or equal to, instead of this we split means instead of this one we prove that 2 n naught by r naught for all norm y less than or equal to 1. So norm ti is less than or equal to 2 n naught by r naught for all I. So ti is a bounded set of numbers, which in other words, ti non-ti is bounded set of numbers, which in other words ti is a bounded as the subset of, ti is bounded as the subset of b of n comma b of b comma f. Hope you all understand, and thank you.